Okay, so here we go for the adventure of a lifetime. Live streaming and filming at the same time. Bernoulli distributions, aka binomial probability, you'll find that those words they do actually mean different things. And one's a distribution, one is the probability calculation method. But, I mean, you're going to find it's fairly interchangeable as well. And you'll find that I probably drift towards calling it binomial probability. So there's some learning goals there, success criteria, we've got a few things to do. You'll know realistically, later on I'll do a couple of examples that are complex, unfamiliar, but this stuff should be mostly pretty familiar procedural stuff as we move forward. So we're going to run through a few things, and I'm going to try and see the first couple of examples I do are going to be done the long way. But I want to set up the process with you as we do it. So let's see how we go. Imagine I roll a dice, and I'm interested in the number of fives I get. Now, first, I just want to recall what we did last lesson a little bit. I'm going to start by drawing the beginnings of a tree diagram for this. Well, I'll draw the whole tree diagram for this one. It's quite small, but later on they get quite big. So here's the tree diagram for 3 dice rolls. Looks like this. I've done a bad job with that. But can I just point out again, and I've walked around the room despite saying this last lesson, and notice that some people are still not conforming. That if you keep these nice vertical lines here, your tree diagram will always be neat. And if you muck up that third little branch on the last column, it will still be neat enough to read. If you want clarity in your work, which is really important, then please consider using those vertical lines for the end of each event. But either way, I've got 5 or a not 5, a 5 or a not 5. I'll do this 7 times, I'm afraid. 5, not 5, 5, not 5, 5, not 5, 5, not 5. And our probabilities are 1, 6, 3, 6. And that follows on. So the first point I want to make here is if you've rolled a dice 3 times, there are 216 possible outcomes, 6 to the power of 3. But because I only care about whether I get 2 5s or 3 5s or 1 5, I'm only dealing with 5 or not 5, which gives me 8 possible outcomes. And it actually gives me overall 4 outcomes. Either, and this is a discrete probability distribution, either I get 0 5s, well, I'm going to turn it around actually, either I get 3 5s, 2 5s, 1 5, or 0 5s. They're my only 4 options. Out of 216 options, I can summarize it down to those particular ones, because that's the focus of the question. So always be aware that we're simplifying the problem quite considerably based on the context. First option I've got is there is one way of getting 3 5s. That's 1 to the cubed. 1 to the power 6 times 1 to the power 6 times 1 to the power 6. There's only one way to get 3 5s, and so it's 1 over 216. Now let's use our knowledge of Pascal's triangle to simplify the next section, and that is that there are 3 ways of 2 5s. So if you follow those branches along, if I follow the branch, they'll all be the same because these are independent events. It's 1 6th, 1 6th, and then 5 6 is my way of getting the not 5, and so this works out to be 6th squared times 5 6th, and in total that works out to be 5 over 200. But because there are 3 ways of doing it, the probability is 15 out of 216. So we're not going the whole hog, we're simplifying things a little bit based on some of our knowledge here later on this lesson. I'll change colour now briefly, and here are my ways of getting just 1 5. I get a 5, not 5, not 5, or if I get a not 5, 5, not 5, or if I get a not 5, not 5. There are once again 3 ways of getting 1 5 only. And remember, Pascal's triangle had 1 3 3 1. I'm really sorry, Pascal. It's going to be like this. It's like when I get to Simpsons rule with Connor and Noel. It's just the way it's going to be. So this is 1 6. That's my probability of success for one of them. I get 2 failures, which is 5 6 squared. This comes out as 25 over 216. But of course, there are it? What's up? Sorry, say that again. Oh, is it? Oh, come on. That's my audio. Now, my concern is that if I unmute my mic, got it on, then it's going to start. Where's my mic? Okay. Is that all right? So there's my 3 ways of doing that. And because they're 20 each, that is 75 over 216. And then the last one is how many ways of getting 0. So I would ask if you do just turn your audio off if you think you need it on. And so I would ask if you just don't have it connected and you're watching me. And not 5 is 5 over 6 cubed, which is 125 over 216. And so this is 125 over 216. A whole lot of groupings of colours, but that's our Bernoulli distribution. Our Bernoulli distribution represents the probability of getting 0 5s, 1 5, 2 5s, and 3 5s. And we've set that up there based on that tree diagram, but a simplified 8 outcomes rather than 16. Does anybody have any questions on that? Once you get complex familiar, complex unfamiliar questions on this topic, this will be really, really important, and it still concerns me that there are 3 or 4 people just staring at their computer screens when I don't think they really need to be. Okay. Are there any questions on that? All right. So there's our little summary, and you can write this down later. I suggest you paraphrase it. It's called a Bernoulli sequence. Each Bernoulli sequence deals with a 2 outcomes. That's why we also call it binomial probability. The bi meaning 2. So each event has 2 possible outcomes, success or failure. We get our context and we divide it into what is success, what is failure. And the other thing is independent. So just keep that in mind. It's also discrete probabilities. If we repeat a trial n times and we can count the number of successes, that's a countable thing. Discrete is countable data. And here's a couple of norms just down here. So our norms are that you'll find that the textbook, that your exam will all use P as the probability of success, and 2 as the probability of failure, and of course success plus the probability of failure will be 1, otherwise we're missing something, so we get this relationship. So in most questions, either contextually or just purely mathematically, you'll be told the probability of success, and then you will have to go and just work out the probability of failure by subtracting from 1. You won't be told both in most cases. So example 1, the probability of me winning a game of squash against, any suggestions? I'm not putting time here to defend himself, but since you're willing to suggest him, that will do. I would never put somebody themselves on that. That would be quite immature, I think. What is the probability I win 3 of the next 4 games? Is the first question. Determine the probability distribution of X, the number of wins for me overall in the next 4 games. So this is a 4-game system. I'm going to do this now logically without a tree diagram because we're building towards binomial probability. So I'm not going to draw a tree, but I do know that B, my probability distribution is going to be X can be 4 wins, 3 wins, 2 wins, 1 win, or 0. And then I'm going to determine the probability that X equals either of those. So that's going to be my Bernoulli distribution, my probability distribution. But I need to do, so let's do part A logically. what is the probability that I win 3 games of the next 4? So the probability of success for me is 0.8. That's been in the question, is equal to 0.8. What does Q equal? Excellent. So the probability of failure is 0.2. And I want to win 3 out of 4. So that means that to win 3 out of 4, I'll just be a second back, so I'm going to try and avoid interrupting questions unless it's a question about the question. If it's a 1-mark question, probably not, but anything more than that, I would be putting in every important piece of information because a lot is applied. So if you don't write down Q equals 0.2, but you use 0.2 later on, fine, you'll get the mark, but not always. So I would be just making every important thing. So hopefully you can all see here that my probability of 3 wins, 3 with the probability of 1 failure. How many ways can I get 3 wins, by the way? So I can get success, 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 and then lose the last one. Or I can get success, success, failure, success. Or I can get success, failure, success, success. Or failure, success, success. 4 ways I could do that. If I drew out Pascal's triangle here, I would have my 4th row would be 1, 4, 6, 4, 1. This would be 4 wins, 3 wins, 2 wins, 1 win, 0 win. The number of ways of getting 3 wins is the second number in Pascal's triangle, or the 4th number, depending on which way you reverse it. Remember, it's symmetrical. It doesn't really matter. So that means that. Who's got a calculator? I don't. 4, 64, over 125, 64 over 625 times 4, 256 over 625. And that equals about what? 0.407, did you say? That. Yeah, cool. Okay, my distribution will be going back and actually working out each of the possible outcomes. So 3 wins implies that I get, and I'll just, you've missed a little bit here, but I'll try and summarize this one. 3 wins out of 4 means that I get the probability of a win 3 times, probability of a loss once, multiplied by 4, because there are 4 ways that I could get 3 wins, as listed here. And in my part B probability distribution, that means my probability of getting 3 wins is 0.4096, or 256 over 625. My probability of x equaling 4 is equal to 4 wins, which is 0.8 to the power of 4. So I don't have to worry about the 0.2. How many ways are there of me getting 4 wins? Just 1. That's if I just get win, 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 win. Yep, perfect. And that equal 0.4096 as well. And you can see that. Look, I've got 0.8 probability of getting 4 or 3 wins, but also my win success is 0.8 anyway. So I'm expecting to win most of the games. 2 wins. The probability that 2 is equal to 0.8. That represents my 2 wins, multiplied by 0.2 squared. That represents my 2 losses. And how many ways are there of me getting 2 wins and 2 losses? 6. And we could sit here and list what Dax has been doing, but we don't need to anymore. We know that it's directly from Pascal's triangle. She's famous and she's in here with So does anybody want to calculate that for me? Because I don't know what that is. 16 times 6, 96 over 25, whatever that is. 0.414, 0.14, 0.1596. Yeah, I'm just rubbing it out, it's being slow. 1596 and 36. The probability that x 1 is equal to 4 ways times 0.8 to the power of 1 times 0.2 cubed. 0.256, and 1 way is what? 1 over 625. What's that? 6666. Is it that? 0.0016. Okay, cool. Any questions? This is still, now we have not drawn a tree diagram with 16 possible outcomes. We've not had to deal with outcomes. We've not had to do anything. This is still a long way in some respects. We're still going to simplify this even more. But here we go. Let me talk about this. This is this particular question. I'm going to summarize what we've just done. I'll bring this with me because I'm recording. So there is the tree diagram. This is what I could have drawn. Just to reiterate again, vertical lines for the events. You can see how clear that is in your exams. I've got pink is 4 successes, 4 wins. That can happen one way. Orange is 3 successes, 4 ways. Green is 2 successes, 6 ways. We're seeing those numbers come through again. So let me just write those numbers in their matching colours. 1, I've skipped 1 for some reason, 6. Orange is 4. Light blue is 4. And again. And if you add these up, you get that magic number 16, which is 2 to the power of 4 as well. That's really nice. You can use that to determine the probability. The probability here is 1 times p to the power of 4. Because if I follow these branches, I get 4 successes. The probability of the orange one is there are 4 ways, p cubed times q to the power of 1. The probability of the green one squared times q squared. Now we all know our algebra, we probably wouldn't bother writing the multiplications. So we could write this down as 4 times p q cubed. You can see the pattern here. This one, I don't even need the 1. I'm just going to write down, and p is wrong. Let's try that again. Q to the power of 4. You can see the pattern now, I hope. And if you can't, ask me. Talk to me so you understand. And then I think that's interesting, and I'm sure that you do as well. So here's some distributions. These are all Bernoulli distributions. If I have one, the probability of success is one way of getting 1 success, one way of getting 1 failure. Interestingly, if I add p and q together, I get 1, which is what I should. 2 events, I get p squared 2pq. If I add those 3 probabilities together, I should get 1. 3 events, p cubed, 3p squared cubed, 3p q cubed. Notice here that it's p cubed, then it's p squared, then it's p, and then there's no p. There's no q, then there's 1 q, then there's 2 q's, then there's 3 q's. And the coefficients are directly from Pascal's triangle. And then we get 4 events, and you could almost certainly work out 5 events. But here's a bit of a summary, a generalization, an n-event system. And we talked in Pascal, in our last lesson on Pascal's triangle, we talked about using combinatorics. That's where you're going to head, because you might use Pascal 4 or 5 events, but beyond that, it gets a bit of. So we're going to use combinatorics instead. So it's an n events. NC0 gives us the first number in Pascal's triangle for the nth row. N0. NC1, p to the power of n minus 1, of 1. NC2, p to the power of n minus 2, p to the power of 2. And remember that most questions are not going to say do the Bernoulli distribution 20 event system, because you've got to write down 20 different calculations and work them all out, wasting your time, and we only care if you can do it once. Most questions are going to say, if I play a game of squash against half times, what's the probability that I'll win 17 of them? You go, that's easy. 20C17 times 0.8 to the power of times 0.2 to the power of 3. Move on. Question done. Easiest marks you'll ever get. You understand what you did. Does that make sense? That was a very leading question, so hopefully it helps. So we're almost done. For example, but to be honest, I've on that topic. I've got to get through a fair bit. So I'm going to run through one more example and just finish the generalization. I'm going to leave the other two examples and do them on Friday. Yeah, so just a reminder that I will have it on here on Teams. This bit in pink, and I and 1 to the power is always equal to 1. If I add those together, plus 2 is 1 and 1 is power. That's really good because you know the sum of all the probabilities should be 1. That's no matter how big the system is. You've got 100 of them, these be 1. If you get 100 of them, you know, this is what can trip people up sometimes. If I'm playing squash against an army, I've got an 80%. And I say, we play 100 games, what's the probability I win 80 of them? And you think, well, it's got to be pretty high because he's got an 80% chance of winning, so he should win. That's what I'd expect him to win. But because there's 100 events and all those events add up, the probability will still be really low. It will be the largest probability, but it will still be something like 0.02 because it will just be the peak of a really flat graph. You know what? You got to flatten the graph stuff now. So if you've got the same area under the graph, we flatten it right out, stretch it out to 100 events, the peak is going to be really low. Tripped up in an exam if it says 100 events, what's the probability of the most likely thing, and it's still really low, expect that 100 together to get 1. But you'll see some questions like that. Examples I've got to run through. So at worst, they'll be on the OneNote by Friday afternoon. But here, and I want to patient 2, you might be told, this is a purely theoretical question, you might be told that X can be modelled by the distribution. This thing here means can be modelled by. My pen is, I need. That means can be modelled by a binomial distribution. At the moment, you've only done binomial. Eventually do normal as well. Can be modelled by a binomial distribution with 10 events where the probability of success is 0.7. That's what that's saying. You might see that in your exam. You might see BI might also just be B. If you see B, it means binomial. If you see BI. And let's do these questions. You need me to stop, but the probability that X equals 3 is going to be equal to 10C3. There are 10 events, and I'm choosing 3 of them. I want 3 successes, times by P, which is 0.7 to the power of 3, times by Q, which is 0.3 to the power of 7. And I am strongly relying on you, and I can see one person is going to help me out here in a second. No pressure, Reggie. It's just a big blank in my video right now. Times 10. Okay. 1 times 10. That's it? Oh, 9.00. 0.7. There are 10 events, so the curve has already been flattened quite a bit, and is pretty unlikely. So I'll take that. Has anybody confirmed it? I've done that. I've written 0.7 to the power of 3. Right. So I want my probability of success to the power of 3. P to the power of 7, that's 7 successes. Like if I go along the tree diagram, that means that I'm going along the success branch 7 times. So it should be 0.7 to the power of 3 times by 0.3 to the well, the generalization, so I've just taken one of these. You have to be logical about your use of P. So X in this case, yeah, the generalization. I just took it straight out of the textbook without really thinking. But can you see the logic behind what I'm saying? Yeah. So 9 point, so I'm just going to write this down. 0.009. That's 10 to the power of -3. Okay, cool. B, the probability that X is less than or equal to 3, and that's going to be equal to the probability that X equals 3 plus the probability that X equals 2 plus the probability that X plus the probability that X equals 0. Now, over here, I don't really want to go through that whole process, although that said, the successes, where the actual probability of success is so high, low number, 2 is going to be even smaller. So I'm not expecting to actually change much on my P of X. But if we go along here, how can we do this in our calculators? I would ask you all to do this for me quickly now, because I've got a couple of pointers that I want to make. So you can either go into your run matrix and then options distribution binomial. You can do that, and I'd encourage you to know how to do that. But if you do it through run matrix, you also know the syntax, and it's not obvious. And it took me a while to work out the syntax. So you have got a second option. You can go into the stats. If you do it through the stats menu, they just put it up on the screen and they tell you what to put in the blank spaces. Whereas if you do it through the run matrix menu, you have to know what I mean by that. If you do it through the run matrix menu, then you have to know that putting in it's going to come up with binomial PD or binomial something like that. You're inputting X as 3. You want 3 wins, N as 10, and P as 7. And there's nothing there to tell you the right order. And if you get it in the wrong order, error. So I would probably do it through stats, but if you get really fluent, you could probably do it through this as well. Now, just as a couple of notes, binomial PD is a point distribution. It's an exact X value, X equals 3, whereas binomial CD is a cumulative distribution. It will give you between 2 values. So in this case, I want X. So for this question here, I'm going to do equals binomial. My lower bound of X is 0, upper bound of X is 3. There are 10 events. The success is 0.7. Tell me the answer to that. And I'm going to leave a pause again and blame you. Is it not working? Do it through, or you can't find it. You mean you can't find it, or it's not working? Out of domain. Well, hopefully that's all right. Let's have a squiz on here. So I go into option, next, probability. I'm in the wrong spot, aren't I? It's in stats, that's right. Okay, distribution, binomial, BCD. I've just said this. I've written down BCD, 0 to 3 to 10 to 0.7, close brackets, enter. Work for me. Oh, okay. So it did work for people. I want them to tell me. 0.0106. Gone. We're struggling. So either know the syntax or know how to do it in stats. Note here, your textbook, and they've stepped it out probably better than I have. So take the time to learn that. Make sure you know how to do it, because it makes your life a lot better. But question C, find the they're not equal to 3. See that this is 1 minus the probability that x is less than and equal to 3, but I have the probability that x equals 3. So if I do minus my answer part B, my answer part B included this question greater than equal to 3, so I can include this equal to 3 in there as well. I'm going to 1 minus this and then add that on. That's going to give me 0.984. You can check it in your calculator for me. On your calculator, it would be B, C, D. Lower bound is 3, upper bound is 10. There are 10 events, and the probability of success is 0.7. Put that in your calculator and check that you get 0.984, give or take. And then lastly is a conditional probability. Find the probability that x is greater than or equal to 3, given that x is already greater than or equal to 2. So I write this down as x is greater than or equal to 3, given that x is greater than or equal to 2. Now, again, you can just use the formula, but I'm just going to zoom in here and talk to you about what this means, and then I'll use the formula. Here is x. Here's my probability that x equals x, and x could be, there could be 10 of them, 9 of them, 8 of them, 7, 6, 5, 4, 3, 2, 1, 0. And I'm saying that we already know that x is greater than or equal to 2. So this bit's been cut out of the question. We want to know what is the probability that it's here, given that we already know it's here. This total probability, that bit, and we're going to divide it by this total probability, that bit, and it'll give us the overall probability. It should be quite large because the probability that x equals 2 is quite small. That formula, I get the probability that x is greater than or equal to 3, and x, is it and or? That formula, is that and or? And? Check it. That formula is on the formula sheet. It's conditional probability on the formula sheet. But the thing about binomial probability is that, oh, actually, yeah, no, it is and. If x is equal to 3 and x is greater than or equal to 2, well then the probability that x is greater than or equal to 3, because this has just got that extra bit. So there's nothing cut out of here. This is in the x is greater than or equal to 2. Don't include that 2. So this will be, I'm doing it slightly elongated, but this should just be the probability that x is greater than or equal to 3 divided by the probability that x is greater than or equal to 2. And I would calculate it almost certainly. So I would do this. PD between 3 and 10, 10 events, 0.7 is my P, divided by BCD between 2 and 10, 10 events, 0.7. If you don't have what you do in your calculator on your exam, you're not really going to lose marks. We're not really expecting that. The last thing we want is keystrokes. But equally, if you want to make and your reasoning, that's not a harmful step to write down. Has anybody worked that out for me? 4. 4 is always good. Now, I estimate x equals 2 comparatively, so I was expecting a number that was quite a large number, but in the probability realm. So a large number in the probability realm means it's just, and that's what we got. So I'm very happy. Are there any questions on that? I'm going to stop there, like I promised. I would encourage you. I'll just stop this.